special type of differential equations, which are Hamiltonian systems. So let me start with introducing the problem. We consider the Hamiltonian system, which is the differential equation of the following form. So this is the first order differential equation, and the right-hand side is the gradient of some potential H multiplied by matrix J. Matrix J here is the so-called standard symplectic matrix, which consists of minus identity formed in this way. So this matrix corresponds to some complex multiplication. So for such a system, we assume that our potential, the so-called Hamiltonian, is smooth enough, which means for us is of class C2. But we also assume that 0, the origin, is the critical point of H. So the condition here is that H prime of 0 is 0. And what this assumption gives us. So if we define the constant function with the value 0, this function satisfies our equation because the derivative of constant function is 0 and the right-hand side is 0. So taking this assumption, we assume that we know one special solution, but the constant solution, very easy one. And the question we want to answer is if there exists any other solutions in the neighborhood of this known one, but we're looking not for the arbitrary solutions, but we want to study the existence of periodic solutions. So we want to study existence of periodic solutions, but in the neighborhood of this given one. Why periodic? Well, first of all, because it's natural. In many natural phenomena, we study periodic phenomena. For example, we want some oscillation, we want some periodic movements of something. And this comes from motivation, because motivation for our research comes, in fact, mainly from celestial mechanics. So probably the most famous is the so-called n-body problem. For such a problem, the Hamiltonian H is given by this formula where Q is position, here P is momentum. So this is the general form of Hamiltonian. And with this Hamiltonian, our equation becomes the Hamiltonian equation of the n-body problem. But sometimes also in the very special cases, there are different kinds. So the very well-known, the restricted free body problem, planar problem, which means we consider it only on the plane, in the rotating coordinate system has the Hamiltonian of this form. So we have some potentials, some functions, we have our differential equations, and we want to study existence of solutions with such potentials. In fact, a lot of potentials in celestial mechanics is of the form similar to this latter one. Namely, we have this first term depending on momentum. Then we have some term which comes from Coriolis forces, and then we have potential which depends only on position. So okay, and we consider many side systems, but this is the classical problem. This is well known, and probably the first and the best known results concerning solutions of such systems comes from Lyapunov, and he considered the system of our form. He assumed again that origin is an equilibrium, but a non-degenerate one, by which it means that this isomorphic, the Hess matrix is the determinant of the Hess matrix is not zero. Then we have to know that we have a pair of purely imaginary eigenvalues, and that this pair satisfies so-called non-resonance condition. I have it here. And what does it mean? That any other eigenvalue is not integer multiply of our first eigenvalue. With this assumption, we obtain the existence of connected branch of non-constant periodic solutions of our system emanating from the origin. And we obtain also the additional information about the periods of solutions. So this theorem has been generalized by many authors. I would only like to mention it here that they are generalizations, and they mainly assume some behavior of eigenvalues. Because if we, for example, assume that the S matrix is positive definite, this is information about eigenvalues. And it can be also the assumption about the signature of the matrix. By signature, we understand here the difference between the number of positive and negative eigenvalues. So, okay, here is only for information. There are a lot of results generalizing this theorem. And then we also want to give some generalization. And we do it with some variational methods, in fact, topological methods, but with variational reformulation. So first of all, so now I will tell only a few things about the methods we use. So first of all, with our first order differential equations, we associate the family of Hamiltonian systems. So introduce the parameter. This introducing the parameter is done by simple change of variables described here. And instead of studying periodic solutions with arbitrary period, we can investigate periodic solutions of fixed 2π period. So it's advantage that we have fixed the period. And now we have the parameterized system. But in fact, this system we can rewrite in the form of operational equation. So we have, taking everything for the left side, we can write it that some operator, differential operator, acting on V and acting on lambda is 0. But the construction of our equation, the form of our equation implies that this our f is of some special form. Namely, it can be we can observe that this is a gradient of some function. So with the additional assumption that that the Hamiltonian has polynomial growth, our solutions can be given not as the solutions of the operator equation, but the operator equation is a gradient one, and where the gradient is of the functional given by such a formula. And we consider this functional on some special subspace, not the space of all continuous functions, but the space of L2 functions with Fourier coefficients satisfying some additional assumption. It allows us to have well-defined derivatives. So we have restricted, summing up, we have restricted our problem to the problem of the looking for the solution of such an equation. It's not a differential equation in this form, but in fact, the differential equation is hidden here. So we study solutions of such an equation with a parameter. But we have assumed that our original differential equation has a solution, and this solution, in fact, any equilibrium of differential equation gives us the family of solutions of this equation 3. And this family, well, can be treated as a half line, because for each parameter lambda, we have a solution. But this solution coming from the constant function, we will call such solutions trivial, and we want to study non-trivial solution. And the phenomena we would like to study is the bifurcation of non-trivial solutions from the set of trivial ones. So what I understand by bifurcation. So I have this family of trivial solutions, and the point of this family is called a bifurcation point of solutions of the equation, if it is an accumulation point of non-trivial solutions. So the solutions which do not belong to our family T. And let me draw it maybe. So this definition can be illustrated as follows. I have here the blue line. In fact, I haven't drawn it here on the for 0, but for the arbitrary equilibrium to illustrate it better. So this blue line is my family of all possible trivial solutions. For each parameter lambda, I have a trivial solution. And then there is one point on this line with a sequence of other solutions converging to this point. So let me observe that this sequence does not come from my trivial line, my line of trivial solutions. And this accumulation point of these non-trivial solutions will be my bifurcation point. But additionally, I would be interested in not only studying bifurcation, but the so-called global bifurcation. And the point is called a global bifurcation point of solutions of the equation if we consider the connected component of this our closure of non-trivial solutions, and either this component is unbounded or it goes back to our family. Let me illustrate it also. So here I have 2 points, and first of all, I have a connected family of solutions. These solutions are in my non-trivial part of solutions. And in this picture, this connected family goes back to trivial family. But the global bifurcation means that, so the global, where the global means here that we know the behavior of our family, not only in the neighborhood of our point, but also we know how this family behaves in the global way. So it can go to infinity in the meaning that it can be unbounded, or it can go back to our trivial family. Okay, but what is easy is to say when can we expect the bifurcation? Because implicit function theorem guarantees that if we have an isomorphism, so we have only one possibility. We can say that there's only one family of solutions, and there will be only solutions from the trivial family. So we can expect some phenomenon of bifurcation only in the points where this operator is not an isomorphism. So from the definition of my sets of global and of bifurcation and global bifurcation, I have the following fact. Each point of global bifurcation has to be a point of bifurcation, and additionally, each point of bifurcation has to be in this set of points for which this operator is not an isomorphism. So I have the necessary condition. But of course, the most important for us is the sufficient condition. So this to study sufficient condition, in fact, we use some tools of equivariant algebraic topology. Mainly we use the theory of the degree for equivariant gradient maps. Equivariant with respect to some compact Lie group G. So we use the equivariant tools. In fact, degree is main tool we use, but we also use the other tools of equivariant algebraic topology. But why equivariant? Because the problems we consider has the symmetric structure just built in the problem. So which symmetric structure? First of all, it is known that the space we consider is a representation of the group S1, that autonomous Hamiltonian system is symmetric always because of in the space of periodic solutions, because of the periodicity. So we can consider the action of the group S1, and S1, element of S1 acts on the function U just by shift in time, changing the time by the angle phi. So in fact, each periodic solution gives us the whole family of periodic solution. Just we can say that by choosing the different initial condition. So our space is the representation. We have the symmetry of the group S1, and with this action, our functional, the functional I have defined for Hamiltonian systems is S1 invariant functional. But in a lot of systems, we can have more symmetries. It can happen when our space, our phase space, is an orthogonal representation of the other group, some compact Lie group gamma I set here. It can happen, for example, some radial symmetry, some symmetry of symmetry groups, when the problem is symmetric. For example, when we have conservative fields, we expect that rotation doesn't change anything. So this is an additional symmetry of the problem. And then our space is not only S1 representation, but is a representation of the more complicated group. So this is the action of this group. So again, the shift in time, S1 acts by shift in time, but then we call it external action of gamma, of symmetry gamma. This allows us to define the knowledge that we have this additional symmetry, allows us to define, to use tools, more sophisticated tools, which can detect more than normal tools, let me say. And this tool is our degree for invariant strong in indefinite functionals. This degree will be denoted by such a symbol. So gradient indicates here that we consider only gradient maps, G that we have invariance, and we compute it for a gradient on H for gradient phi of H for some subset omega, and this degree is an element of the so-called Euler ring. Well, Euler ring is the structure which can be treated as it's not defined, but treated as the module, Z module, generated by each conjugacy classes of closed subgroups of our Riemann group. So if we have a group with a lot of conjugacy classes, the structure of this Euler ring would become more complicated. And for each each conjugacy class, we will have here coordinate in this Euler ring. So we have defined the degree for such functionals with Rybicki in 2011. And yes, and this degree allows us to define the bifurcation index. So what is bifurcation index? We take the point in which we can expect bifurcation. So the point in our set P of phi. Then we choose epsilon in such a way that this point in P of phi is the only one point. So we don't have any other points suspected to be bifurcation point. Then for a sufficiently small disk, we compute the degrees. And we have the difference of the degrees. So in fact, we for a point in which we want to check the bifurcation, we compute the degree above and below. And if the degree change, bifurcation is non-trivial, and we expect bifurcation. And in fact, this is the theorem. The theorem says that if the bifurcation index is non-trivial element of our Euler ring U of G, then we can expect bifurcation. So if I consider, let me start with the system, I will say non-equivalent systems. So the system in which I do not assume additional symmetry. The only one symmetry I have is the symmetry given by the periodicity of solutions. So I have only the action of the group S1 on elements of this space. So in the case of G equal S1, the elements of our Euler ring are not so bad because they can be identified with such sequences. Because all conjugacy classes consist of one element, and we know all closed subgroups of S1, and the subgroups are exactly S1 and ZK for K natural. So we have such sequences, and for such elements, we can compute exactly the degree. We can compute the degree for the functional corresponding to Hamiltonian systems, and we have described this in this paper. So in fact, what we obtain is the formula for the bifurcation index. So let me see this formula. As I said, this formula is in Euler ring, so it would be a sequence of integers. First integer is 0 here. We don't have anything on the first coordinate, but then on each other coordinate, we have we multiply the Brouwer index of H prime by this big thing. But this big thing is quite an easy one. This is the change of the Morse index. So this is the difference of Morse indices of the matrix TK, defined as follows. For lambda naught plus epsilon and lambda naught minus epsilon. So in fact, we compute the change of the Morse index of such a matrix. In fact, this matrix has a 2 times bigger dimension than our Hamiltonian system. So we only have to know how to compute the change of the Morse index. And this bifurcation index also coincides this with the index defined by Dancer and Rybicki in this paper. So with different methods, they also obtained a very similar bifurcation index. And they have proved that for such a bifurcation index, if this bifurcation index is not 0, then we obtain the connected branch of periodic solutions of our Hamiltonian system emanating from 0. So what does it mean? Connected branch of periodic solutions? It means that we obtain the existence of the whole family of periodic solutions, so infinitely many periodic non-constant solutions in the neighborhood of our constant solution. And in fact, only problem is to compute the change of the Morse index, and I will show it briefly how to do it for the systems with Coriolis forces. So as I mentioned at the very beginning, this is the kind of systems we obtain quite often for celestial mechanics. The example is the restricted free body problem, planar restricted free body problem. So the systems with Coriolis forces would be systems with potential Hamiltonian H given in the very special form. So we have the term depending only on momentum. Then we have the term which comes from Coriolis forces, this scalar product P and Q with the matrix alpha. And this matrix alpha will be different in different cases. But I should mention that we consider such systems only for N2 or N3, which is natural in celestial mechanics because the phenomena, well, N3 is most natural because phenomena they consider are in three-dimensional space. But sometimes we can consider this phenomena on restricted to the plane. So it would be N2, N equal 2. And in this case, our matrix alpha is just a symplectic matrix. But in the case, three-dimensional case, which will be called spatial case, this matrix alpha comes from the planar case. So additionally for N3, we assume that V in the neighborhood of some plane satisfies in satisfying way. So the partial derivative 4 points on the plane is 0. And we consider only equilibria on some given plane. So let me start with case 2, n equal 2. And since n equals 2, we have 2 eigenvalues of this matrix. And if we have 2 eigenvalues, well, each pair of eigenvalues can be put somewhere on the R2 plane. So the whole plane, the whole set R2, can be divided into some subsets. And we can obtain, I will denote those subsets by R1, R2, etc. And some lines here I will denote by C1, C2, C3, etc. And the results we obtain are the following. We can say if there exist or not solutions depending on in which region the pair of eigenvalues is. So if we compute the pair of eigenvalues, we can just check in which part of R2 this pair of eigenvalues lies, and then we can say, that if this pair of eigenvalues, so this is the pair of eigenvalues of our potential, this part of potential depending on position. So if the pair of eigenvalues lies in the region R1, let me go back. So this is the region R1 here. So we know that there's no branch of periodic orbits, no branch emanating from the equilibrium. So we have a non-existence result. But if this pair of eigenvalues is in one of the regions R2, R3, R4, then there is a connected branch of periodic solutions emanating from the equilibrium. So in those regions, we know that there is a branch of periodic solutions. The last question is what happens on the lines. So if we have on line C3, we have to assume something additional. So we give assumption of the so-called Brouwer index, the Brouwer index of this of V prime minus identity. And if we know that this Brouwer index is not trivial, then again we obtain the existence of a connected branch of periodic solutions. And in the similar way, we can prove the existence for n equals 3 in the spatial case. So again, we consider only the pair of eigenvalues because we assume that the third eigenvalue is positive. So we consider only two remaining eigenvalues, which carries our case to the two-dimensional case. So we are again we are going back to the planar case I have just considered, but in this spatial case, this additional eigenvalue implies that in each part of our picture we have solutions emanating from the equilibrium. So this is there's a result from the paper we have published last year, and we have also. I would also like to show example, but before example, a small comment. This was done because we have not so many eigenvalues. In fact, we had two eigenvalues or three eigenvalues, but in the general case of n, our Hamiltonian, well, the matrix is more complicated. The change of the Morse index is more difficult to compute, but we can obtain the results similar to the ones I have just described. But we have to use more complicated tools to study the change of the Morse index. We use the so-called normal forms of Hamiltonian matrices, which is for Hamiltonian matrices can be treated as a counterpart of Jordan matrix theorem. So we have just formulated theorems for this case in the paper we have just finished and sent for publication this paper. But okay, example. I would like to show the example of the systems of Coriolis forces I have just described. So the example would be the restricted triangular four-body problem. By the restricted problem, we understand the problem of studying the motion of a massless dead particle under the force of gravitation of other primers. So we are only interested, we restrict this fourth particle to the massless one. But three other primers, of course, have masses, have positive masses, then would be M1, M2, M3. We assume that these masses lie in the vertices of an equilateral triangle, which is called the Lagrangian triangle. This is obtained from the solutions of free-body problem. So if we have the solution of free-body problem and then we have the fourth body in the moving in this would be our restricted triangular four-body problem. And the three big masses rotate solidly around their center of masses at constant angular speed. So this problem is of our form. It can be modeled by our system, where I put only here this part of Hamiltonian depending on momentum, on positions, I'm sorry, on position. So this is the formula, and it's defined, it's not defined on points Q1, Q2, Q3 because of collisions. And okay, so this is the illustration of this. These points, this red, magenta, and say yellow points are the positions of my masses, and I want to study the movement of massless particle here. But if we have this triangle and we draw the lines, the lines divide our plane into subspace, which are denoted here. So the T is the interior of my triangle. Then we have D1, D2, D3 just outside the triangle, and O1, O2, O3 also. And the theorem we can prove is for any traces of the masses which satisfies the their sum has to be in some units equal to this number. We know that there are at least 7 regression points for this problem. So this corresponds to our stationary solutions. 7 because we have 7, let me go back, 7 regions which are important. So regions T, O1, O2, O3, and D1, D2, D3. And what is important for us, that from these 7 planar libration points can be chosen so that there are global branches of closed orbits emanating from all of them. So we obtain at least 7 branches of periodic solutions. So we have a lot of families of periodic solutions. Okay, but in fact, it was obtained, so we have obtained 7 branches of periodic solutions only using the symmetry given by periodicity of solutions. But if we take into consideration additional symmetries, we can obtain more. So in the last part of my talk, I would like only to just say some information about what can we obtain if we take into consideration more symmetries. So as I say, instead of only S1, we can consider the symmetry of gamma times S1. So this is the problem we are currently studying with Rybicki and Stepaniak. We consider the Hamiltonian system, again, Hamiltonian systems coming from celestial mechanics, some generalized Henon-Hayes system and other systems with symmetric potentials. So assume the systems has symmetric potentials with some gamma symmetry. In fact, we concentrate now on S1 symmetry. So we have S1 symmetry of the in the domain and S1 symmetry because of periodicity of solutions. So it gives us the torus symmetry of the system. And we can obtain, again, we compute the bifurcation index, but in this time, the bifurcation index is not an element of the Euler ring of S1, but the Euler ring of the torus. And why to do it? Because you can show that we have examples that the bifurcation index computed only with the use of S1 group doesn't imply bifurcation. But if we compute it in more sophisticated tools, we use the complicated Euler ring for the torus, we can obtain bifurcation even in cases when which are not detected by non-equivariant tool. So we study now the systems with torus symmetries, but this is for the point. So we assume that okay, we have symmetric system, but again we study only the point. But it can happen that such points comes into orbits, because if you have the critical point of the symmetric functional, each point would be critical again. So we have the index, and we want to study the index for the orbit. On my picture, when I illustrated bifurcation, it was that I have illustrated in the first case the line of trivial solutions, but we can obtain something like an annulus of the trivial solutions, or the other set of trivial solutions consisting of the orbits. So we want to study also bifurcation from the orbit. And in fact, we have developed the tools for this. So we have developed this for tools for the degree for the orbits of solutions, but we have used this for partial differential equations, namely for Neumann problems. We haven't used this for Hamiltonian systems yet because the computation of the bifurcation index is complicated. But we have started to do it for a bit easier system, which is the Newtonian system. So the Newtonian system is the system of the second order differential equation of this form. We assume that we have a gamma invariance here, and with some assumptions for this again, for eigenvalues and for the way the group gamma acts, we have obtained the sequence of solutions bifurcating from the orbit. So the thing we are going to do next is to do it to obtain not only the sequence of solutions, but the connected set of solutions and describe the behavior of the set in the infinity. And the last thing we would like to, we want to study, in fact, we study, is to study not only Hamiltonian systems, but we want to study also connected problems, in which we also have, so the problems which in a mathematical way behaves similarly to our Hamiltonian systems, but they have more complicated structure and they have more symmetries. So the kind of problem we are currently studying is the problem of the multi-component Bose-Einstein condensates. So if we use the Gross-Pitayevsky model, we obtain that the energy of this this model can be given by such a formula. And okay, so we are looking here, you know that the solutions here, U, are some wave functions. And we, in fact, this gives us the problem quite similar to the problem of Hamiltonian systems. And but the symmetry here is even more complicated because in the case we are studying, which is the case n equals 4, and omega being the unitary ball, the energy is has a large group of symmetries. This group is O3, so this is orthogonal group of dimension 3 times a symmetry group 4, S4, times 4 copies of orthogonal group of dimension 2. This symmetry comes from interaction and also from the symmetry of configuration of this problem. So this symmetry comes in the natural way from the problem, but there is a lot of symmetry, and the algebra here is complicated. We have a complicated ring, but still the results we can obtain, not everything yet, but something what we can obtain are results about the existence of periodic solutions in the neighborhood of some given solutions, and we know the information about the isotropic groups of the solutions. So we know the symmetry of obtained solution. This is our most current work, and rather something what is our dream than something what we have done. But that is all I wanted to say today, and thank you for your attention.
So thank you very much for a very interesting talk. And now this is time for questions. So who would like to ask a question? So I just give a chance for other people to ask some questions, because I would have a lot of questions here to this talk. So my first question would be, I think that you have said that the bifurcation point is an accumulation point of some non-trivial branch, and this branch has been discrete exactly on this picture. So do we have such situations, or the generic situation is that this is a continuous branch?
Well, it depends on the smoothness of the potentials we have. So in fact, it's rather the thing that what we can prove than what occurs in the natural phenomenon. So in the phenomenon, when for example, when the potential is analytic, we can expect very smooth branch. But when we don't know too much about potential, or it has some, for example, collisions on some points, we can expect that we will not obtain. So it's rather the question of what we can obtain, that what we really know is in the nature. Okay, so it's so for smooth potential, the answer is for smooth potential, I would expect smooth families.
Mm-hmm. And can we predict something about what happens to stability of this constant solution after the bifurcation?
Yes, this is the very natural question. And this is the question that people who apply the things naturally ask. And well, it's not, in fact, it's not the thing we study, but we know something. Our problems are connected with the problems of stability, but with linear stability. So it's with these methods, we can say only something about the linear stability. So the change of linear stability comes from changes in eigenvalues, the number of positive, negative. And in fact, when we study the change of the Morse index, we study the change of the number of eigenvalues. So usually bifurcation comes from the studying of change of stability. And on this bifurcating branch, we have to use very different methods, because we know that linear stability is not the sufficient condition for stability. So the methods has to be very different, but I know there are researchers like this, so something can be said, but not with these methods.
Okay, and you know, when you thought about using this additional group of symmetry gamma, so this group has to be continuous Lie group, or it can be as well a discrete.
It can be discrete groups like ZK. Let me on the last slide. Okay,
yes,
exactly.
So
here exactly. I have O3, but I have S4 here also. So groups like S4 are very natural here, because the configuration of, say, atoms or particles is symmetric. So this gives the symmetry, because we somehow can interchange my positions here. So it is very natural for discrete groups to appear. Yes. So we study. In fact, studying discrete groups is easier. This is more, we can say, usually the structure of the groups. I know even about computer programs computing the coefficients of the degrees, so we can check, because we have only a finite number of possible subgroups, etc. So yes, it is studied. Yes, we do it also. So here is the example that the discrete group appears only as an example, but in the results here, I haven't put the details here, but here we consider also the discrete groups. So yes, so this is the ZK symmetry, additional S1 symmetry given by periodic solutions. So yes, we can obtain results, and we do it also, yes.
Because in this three-body problem, we also have a discrete solution. Yes, we have a Z3 solution. Z3 symmetry group. Yes, and have you applied this gamma group, this discrete gamma group, or only S1?
No. In these results, I have so in this paper about yes. So here, yes, this is the symmetry, but here we have we could obtain results without using additional symmetries. So the periodicity of solutions, this S1 symmetry gives us a lot of branches. I mean, for such a problem, because we usually use problems, the problems are studied by many researchers, namely a lot of results with numerical methods. So we know that we can expect what we can expect, and but only numerically or computer-assisted proofs. So with these methods, not taking into consideration the Z3 symmetry, we obtain almost everything what we could obtain. So it would not give more here to take into consideration the Z3 symmetry. But yes, we can interchange the positions of this. But in fact, if we do not assume that the masses in this triangle are equal, I haven't assumed this. I said here that I have three masses, but not equal. So in the general case, there is not this symmetry. But if we assume that the masses are equal, yes, we can use another symmetry. But our result is for any choices of masses, not only for equal ones.
Okay, so thank you for your answers. Maybe maybe it's enough questions from me. So maybe another person could ask a question. I see there are no other questions, so thank you for this very interesting talk.
Thank you very much.
Wait for new announcement about new DAMSI seminar.
Thank you.
Thank you. Bye bye.
Thank you. Bye.